Yes, so which is what we're going to have here. So that's why our first characteristic of a conductor in equilibrium is that the SHA is equals to 0. So for that one, we're clear. So the second one is that potential is equals to a constant. So I'll try to explain on that again. So we have potential is a constant. So for potential is equals to a constant, we have we drop something the other time which says our SHA is equals to our SHA is equals to negative grad V. So we're going to have negative dV, so to say, over dx, whichever Cartesian, whichever repair you want to use. So we have dz in this case. So we say that SHA electric is equals to negative grad of V. So this is from our expression, this expression. We have this expression, E is equals to negative grad V. So we have this, which we can replace by this. It can be in any Cartesian, so you can write the whole expression, but to just get the first part. So if we have our SHA is equals to 0 in this case, so if we have our SHA is equals to 0 in this case, we're going to have 0 is equals to negative dV over dz. And if you make dV your subject of the formula, we're going to have dV. We're going to have dV is equals to 0. And then you know that for you to have V, you have to integrate both sides. So we're going to integrate both sides. We're going to have, when we integrate this side, we're going to have V, sorry. So we're going to have V is equals to integration of anything is equals to the integral plus a constant. So we're going to have integration of 0, which is 0 plus a constant. So we can conclude that for a conductor in equilibrium, given that our SHA, establishing that our SHA is equals to 0, as we've discussed, we're going to have, there's a text, Lawrence, last.
No, I sent that a long time ago when you said this is our last class.
Yeah, so after this, we're going to have this. And then we can, from here, we can conclude that our V is equals to a constant for a conductor in equilibrium. So our V is equals to a constant for a conductor in equilibrium, which is what we have established here. So I hope that part is clear. And then we move on to, okay. We move on to the next characteristic. So we go to the next characteristics. So we move on to the third one is that, so this is what they were trying to explain here, the second point, which where our potential is equals to a constant. And then the third point is that density volumic décharge. So the density volumic décharge is equals to 0. So as I said in the previous drawing, let me just draw it again. So if I have a spheric conductor, in this, I have a spheric conductor, the density volumetric discharge inside is going to be equals to 0. So we can also prove this from our equation, the Poisson, or the Gauss theorem, which we have here. So we have divergence of E, and then we have established that our E is equals to 0. So if we have our div of E, we have our div of E, or we have EDS, which is our EDS. So we have our EDS here is equals to our charge over our, is equals to charge density over epsilon 0. So if we've concluded that our E, we are going to have this is equals to our E, which is 0. So 0 times ds is equals to 0, is equals to rho over epsilon 0. So if we do this, before we actually even replace with a 0, we can conclude. So, but if we do this, we have rho is equals to 0. So our density volumetric charge is equal. I'll just go on and read the explanation. So we used the equation de Poisson, where the div of E is equals to the density volumetric charge constant over the permittivity, which is epsilon naught. And then we have concluded that our density volumetric charge is equals to 0 from what I'm just explaining. So if our div of E is equals to 0, we can make the constant, the rho constant, the subject of formula. So we're going to have our rho. We're going to have rho. We're going to have rho is equals to div of E. We're going to have div of E times epsilon 0. So if your div of E is equals to 0, then you have your rho equals to 0 as well. So yeah, aside moving on from that, this is the explanation that they gave, just explaining the same thing that I'm talking about. And then the next part, which is so here we've concluded that the density volumetric charge is equals to 0. Then la série resultante signifie que tout élément de volume, il y a autant de charges positives que de charges négatives. So si le conducteur est chargé, cette charge non composée ne peut exister qu'à la surface du conducteur. So this drawing right here, so in effet, dans une couche très mince, quelque Coulomb assimilé à une distribution superficielle de charge. Dans cette couche de d'épaisseur, le champ n'est pas nul, il ne peut être que normal à la surface. So here what they're trying to tell you is that if we have a spheric conductor, let me just draw that again. So if I have a spheric conductor, or any shape that you want, it can be an irregular shaped conductor. So if I have a spheric conductor and I have it's positively charged, so inside I have positive charges. So inside I have positive charges, infinitely small. So yeah, inside I have positive charges. So we know that like charges, oh yes, like charges repel each other. So these charges are going to repel, they're going to repel each other. Then as a result, they're going to be found on the surface of the conductor. So the positive charges are going to repel each other in the surface of the conductor when it's at equilibrium. So if they repel each other, consequently, they're going to be found on the surface of the conductor. So we're going to have them on the surface of the conductor. We're going to have them on the surface of the conductor. This is what they're explaining here. And then the field, we already talked about field. Field is always outward, out of the charge. So the direction of the field is going to be outwards, making them normal to the surface of the conductor, which is what they're explaining here, which we have there. So this is what they're explaining. So we have the charges. This is a surface, the surface of a conductor. We don't know, they didn't really finish the drawing. So this is the drawing. We have a conductor here. And then we have the charges, the positive charges that have repelled each other from inside and subsequently find themselves on the surface of the conductor. And this is what we have here. And then we have the direction of the shaft. And then inside they're indicating that the E is equals to 0, the V is equals to a constant, and the rho is equals to 0, which is what I'm from explaining, talking about the characteristics of a conductor in equilibrium. And then we move on to, so what was being explained here? Okay, so we have, a minute. Okay. Okay, so there's a mistake. Okay. Okay, so there's a mistake with the, let me just correct it. There's a mistake with the pages. So this one is supposed to come next. Let me see if I can correct that. Okay, so this is supposed to be the third page. Okay, so from here, I'll send you a corrected one with the corrected order of pages. So from here, we have discussed the three characteristics of a conductor in equilibrium. We've said that the shine is equals to 0 inside the conductor, the field, that's the field. And then we've discussed that the density volumic the charge is equals to 0. And we've discussed that the potential is also equals to 0. So now we're going to move on. So now we're going to talk about the same conductors. So they're saying a case where we have a cavity in a conductor. So I'm going to give an example of a car. A car is made up of metal. Let's say a car is a conductor. So it's got a cavity inside. It's hollow inside. There's space inside. So you as a person in the car is being protected from, let's say we have lightning outside. So you in the car is being protected from the lightning and everything that's going on outside, from the field, the lightning that's being caused by the electric field, because inside the field is equals to 0. So inside the conductor, we have a hollow sphere where the field is also equals to 0. So this is what they're saying here. So because while you have a cavity in a conductor in equilibrium, so if you have a cavity inside the conductor that is in equilibrium, we say the cavité ne contient pas de charge, la surface intérieure est équipotentielle. Le potentiel dans la cavité ne peut être que constante la continuité, c'est potentiel est celui du conducteur. So, le potentiel est étant une constante, le champ est nul at 2 points de la cavité. So it has the same characteristics. So if you have a cavity, which is like a hollow shape inside a conductor, so we can say that the potential is the same as the potential of the cavity is the same as the potential of the conductor, which is equals to a constant. The field in the cavity is equals to 0, and the cavity does not have any charges. So the champ also is equals to 0. So which was this petty explanation that we have here. So we have resume the propriété d'un conductor in equilibrium. So we have that simplified version. So we have dans un conducteur plein ou dans un conducteur creux dont la cavité ne contient pas de charge lorsque l'équilibre est réalisé. Le champ est nul, so we have the field is 0, le potentiel est constant, and the surface exterior du conductor peut porter une charge non composite. So we have, if this is a conductor here, a drawing of a conductor, we know that the E is equals to 0, the V is equals to constant, and the density of volumic, the charge is also equals to 0. So if we have another conductor with a hollow inside or a space inside, we have the E for the big conductor is equals to 0, the V is equals to a constant, and the density volumic, the charge is also equals to 0. And then for the hollow guy, also the space inside the conductor is also going to, the properties are also going to apply. So we have the E is equals to 0, the V is equals to a constant, and it doesn't have any charge. So the next part is talking about if we have, so we have champ au voisinage immediate d'un conductor in equilibrium, theorem de Coulomb. So now we're going to be talking about if you are told to calculate the field that is outside of the conductor, at a point outside of the conductor. So if I have, this one will need a little explaining. Okay, so if I was talking about champ au voisinage immediate d'un conductor in equilibrium, so I'm talking about the field close to a conductor in equilibrium. So if you're trying to find the field close to a conductor in equilibrium, so I'm going to give an illustration. If I have a conductor in this form, and then I have charges on the surface of the conductor. I have charges on the surface of the conductor. I have positive charges. We can have negative. So I have positive charges on the surface of the conductor all around. So I have positive charges. I have positive charges. I have positive charges. Yeah, so I have positive charges all around the conductor, and then I'm trying to calculate the field, or to talk about the field that's at this point. So we say this point is P, outside of the conductor in equilibrium. So what we're going to do right now, we're going to talk about how we find the field. So if we're told to calculate a field outside the conductor, which I've located the point here. So now we're going to introduce a cylinder, because now we're going to have to use theorem de Gauss. So at this point we have we're trying to calculate the field at this point. So we're going to introduce a cylinder around that point. So we're going to introduce a cylinder around that point. Introduce a cylinder around that point. So we're going to have a cylinder. Okay. So we're going to have a cylinder around that point. So if I have a cylinder around this point, let me just try to magnify what I'm doing. So I'm trying to, this is the area that I'm going to draw. So this is the area that I'm going to draw. So let me draw it again. I'm going to have this area, I'm going to have it on this part. So I have the positive charges here, I have the positive charges. I have the positive charges. Now I'm trying to calculate the field here. So I'm going to have my cylinder. So you can introduce a cylinder as long as, because we're using Gauss, we're going to use the Gauss theorem to calculate our field. So you can use any closed object. So here I've chosen to use a cylinder. So you can use a box or a square conductor. So I'm going to have a cylinder here at the surface of the conductor. So if I have a cylinder at the surface of the conductor, we have this. So these charges are producing, these charges, there's the electric field acting from them. So we have this as the electric field acting on this and this. So we also know that there's also charge here. So we're going to have the electric field moving in that direction. We're going to have electric field moving in that direction and so forth. So it's safe for us to say that here, this part, so we assume this charge is arranged in a line. So we assume this charge is density surface 6. So we're going to have along a certain surface. So it's along that surface. So we're going to have the total charge. The total charge of these charges is this. So we're going to have, we're trying to find the shunt at this point where we've drawn this cylinder that we have here. So we know that we're going to have flux because flux is the rate of flow of electric shunt. So from inside the cylinder, we do not have any charges. So the field is just going to be on top, on the surface of the cylinder. So for us to have the E here, we're going to use a theorem de Gauss. So we're going to have E ds is equal to, so the charge at this part of this of the surface, at this part of the surface, we won't say it's this because it's just a small part of it. So we're going to use this times the area at that point of the charge. So we've gotten, sorry. So because we're trying to find the field at a certain point of this area, so we're going to get the charge. We're going to be using just the charge at this area. So that's why we've used that, and then over this epsilon 0, which is what we have. So our normal equation is supposed to be this, supposed to be EDS is equals to charge over epsilon 0. So the charge enclosed over epsilon 0. So which is what we have here. So, oh my God. So, okay. So after this, we're going to try and simplify our equation that we have. So here we're going to have, so if we try to make E the subject of a formula, our ds, try to simplify the whole expression. We're going to have our ds, and our ds is going to cancel at some point, and then we're going to remain with E is equals to the charge, the constant over epsilon 0. So we're going to have E is equals to that over epsilon 0, which is what they were trying to explain to us here. So we're going to read, nous allons calculer le champ électrique at a point very close to a conductor in equilibrium. So we already know that the champ is normal to the surface. So as I explained here, the champ is always normal to the surface, always going in the outward direction. And then this was a very complicated diagram, even for me to understand. So I tried to explain it using this simpler way. So hopefully you understand how at last from here we ended up having our simpler equation from here, which is E is equals to the charge over the epsilon 0, which is what we have here. So I'll send you the arranged in which they are arranged. Sorry about this. So from everything that I explained here, they ended up having a simpler way of calculating the SHA, which is just having your SHA is equals to the constant over the epsilon 0, which is actually our theorem, the Coulomb. So yeah, this is what we have here. When finding the field at a point very close to the conductor in equilibrium, this is what we have here, which is simply the theorem, the Coulomb. Yeah, so this is what we have here. So which is that explanation. And here they're talking now, they're introducing the direction. So we have the direction. So we've said that the E is usually normal, is usually a normal to the tangent. So the E is usually coming out like this. So if this is a round surface, we'll see that at almost every point, the E is in the direction that is normal to the tangent. So this is where we have the vector unitaire coming from the UN vector unitaire. So E is equals to our constant over epsilon 0 U in the direction UN if we introduce our direction. So are there any questions up to here? Okay, we continue. Yes, so this is what I have here, which is everything that they were trying to explain. And then the next part is now we're going to talk about the Earth as a conductor. So we know that the Earth also acts, also can be qualified to be called a conductor, and then the potential of the Earth is equals to 0. So how is the potential of the Earth equals to 0? So usually when so there are two explanations that I can give for why the Earth has a potential of 0. So other from our equation of potential, we have V is equals to 1 over 4 pi epsilon 0 Q over R over R. So some scientists say because the radius of the because the radius of the Earth can be up to infinity. So you know that everything, if we have a constant, so if our R is up to infinity, we know that everything down here will be equals to infinity. So we're going to have Q over infinity. Yes, we're going to have Q over infinity, which is a big, it's a very huge radius of the Earth. So we're going to have this, you know that from your math, anything, a small constant over infinity is equals to 0. So that is the first reason that I know. And then the second one, they say because the clouds induce, the Earth has a negative charge, and then the clouds induce a positive charge. So there's a neutralization of charges, and our potential on the Earth is ended up being 0. So yeah, so this is the first one that I know. And then the other one, they argue about the charges, the different charges on Earth and the sky, the clouds. I mean, the charges that are induced by the clouds. So this is what I say comme conducteur peut-être considéré comme un énorme conducteur in equilibrium au potentiel invariable. Il est commode de prendre un potentiel égal à 0. So the potential of the Earth, or when the Earth is acting as a conductor, is equals to 0, which is what we have here. And then our next part is where we talk about influence electrostatic, where we I think we did this in physics, where we talk about induced charges and inducing charges and everything like that. So here we soit un conducteur est isolé initialement et neutre. Nous approchons un conducteur B isolé mais chargé. So if we have a neutral, let me just draw it. So if we have a neutral, conductor, so it has both the positive and the negative charges, and we have a positive conductor. So this is the final. So if we have a neutral, so it has both positive and it has both negative. So this is a neutral conductor. A neutral conductor. We have negative, we have positive. We have negative, we have positive, we have negative. So this is a neutral conductor that is isolated. Not have given the name A, and then we have a charged conductor, a positively charged conductor. So we have a positively charged conductor. It's been positively charged. Positively charged. You have a positively charged conductor. So what's going to happen here is that if we move this conductor B, towards conductor A, we're going to induce the charges on the neutral conductor. So the neutral conductor, we're going to see that the negative charges are going to be attracted to the positively charged particles in B. So as a result, we're going to have what we have, the drawing that we have here. So we have this. So we're going to have negatively charged particles coming on this side of the conductor, and then because of these positive charges, and then the positive charges are going to get on this side of the conductor, are going to get repelled and are going to be on the other side of the conductor, which is what we have here. So the negatives are going to be drawn towards, if we bring the conductor B close to the conductor A, so we know that the negatively charged particles are going to get attracted to the positively charged, and then this is the drawing that we have here. And then the next part is the explanation of what is going on. And then, but if we introduce the ground, if we connect one of these conductors, we can connect this conductor to the ground, and we know that the potential of our ground is equals to 0. So we connect this guy to the ground, earth it. So we connect this one to the ground. We're going to have so we're going to have So we're going to have a conductor and the negative charged particles that have been attracted. So we have the negative charged particles on this side, and then the positive charged particles are going to get attracted to the earth, and our potential is going to be 0. So because our potential on the ground is equals to 0, when we earth this conductor, the positives are going to be drawn towards the earth, and then we're going to have a net, or we're going to have more of the negative electrons or the negative charged particles on this conductor of A. So if we have a neutral conductor, we have both positive and negative. We introduce a positively charged conductor to the neutral charged one. We're going to have the negative being induced, being attracted to this charged particle. And then if we earth the conductor, the positive that on the other side that have been repelled are going to get attracted to the ground. So they're going to get moved to the ground. So we're going to have a net of this conductor is going to be negative. So we're going to have A, which has more of the negative charged particles on it. So this is what we have here, which is what was being explained here. And then here's what we see when we ground the conductor. We're going to have more of the negative charged particle on the conductor, and then we're going to have the B after the A has been grounded. So after the A has been grounded, we're going to have that. So are there any other questions on conductors and everything? Are there? Okay, so we've during the previous weeks we've talked about charges. We've talked about the positive and the negative charges. We've talked about the charge. You know that the charge for an electron has a charge, a negative charge. A proton has a positive charge, and a neutron is And then we've also talked about the loi de Coulomb, where loi de Coulomb. Let me just get you through a petit rappel. So the loi de Coulomb. So we've talked about charges. We've talked loi de Coulomb. Loi de Coulomb is when we're trying to find the force. So loi de Coulomb also, the ones tell you to state what loi de Coulomb is. You just have to know these things. When they tell you to use loi de Coulomb, you know which expression you need to use. When they tell you to use theorem de Gauss, you know which expression to use. So loi de Coulomb, which says that magnitude of an electrostatic force between 2 point charges is directly proportional to the product of the magnitudes and inversely proportional to the square of the distance between them. So we discussed that our expression for loi de Coulomb is this. So if we're trying to find the force between 2 point charges, so we have force is equals to 1 over 4 pi epsilon 0 Q1 Q2 over R squared. So I believe most of us remember this expression, R squared in the direction of U. So this is our loi de Coulomb. And then we went on to talk about electric field, which is SHA. So electric field is force is so electric field is the force per unit charge. Direction of field is direction of the force it would exist on a positive. So if we have a positive charge, we talked about SHA. If we have a positive charge, we know that the field will be outwards. The field will be outwards. We know that if we have a positive force, the field will be outwards, and if we have a negative charge, the field will be towards the charge. Same applies with the force being produced by by the charge. So here we have positive, we have the E moving towards the charge. So just by the direction of the field, if you have any question and they give you the direction of the field, you can know whether you're dealing with positive charged particles or negative charged particles. So we have the E. We have the E, which is our champ. Yeah, then we also went on to, sorry, went also to talk about the theorem de Gauss. So theorem de Gauss, we talked about the total electric flux out of a closed surface is equal to the charge enclosed divided by the permittivity. So we talked, our equation for our theorem de Gauss was this. So these are the most important equations that you should know. So we have theorem de Coulomb, theorem de Gauss, which is what I'm about to write right now. So I have our theorem de Gauss is when we're trying to find the flux, and we know that flux is the rate of flow of electric field. So if we have charges, and we have electric field passing through a paper, let's say a paper or any other surface. So the rate of flow of electric field on that surface is what we call flux. So our flux is equal to this, which is equals to this, E ds. E ds is equals to Q over epsilon 0. So that's our theorem de Gauss. So yeah, so the theorem de Gauss is states that the total electric flux, which is can be represented by this symbol, or E ds, is equals to the charge enclosed by the divided by the permittivity, or the epsilon 0 of the of the surface. And then we went on to talk about potential. So potential is the amount of work needed to move a unit charge from one reference point to a specific point. So the amount of work needed to move a unit charge from one reference point to another specified point or another specific point. And then we had our equation for a potential. Potential was equals to 1 over 4 pi epsilon 0 Q over R plus a constant. And then we talked about conductors, and conductors, we talked about the materials where electrons move freely, and we talked about the characteristics of conductors in equilibrium. The conductors in equilibrium, if the charges or the charges that are supposed to be moving freely or supposed to be mobile are at rest. And then we talked about the characteristics of the conductor. The charge is supposed to be equal to 0. The potential is supposed to be equal to the potential is supposed to be equal to a constant, and the density, the charge volumic is supposed to be equal to 0. So are there any other questions? Are there any questions so that we end the video? So if you have help or if you have questions, I think I sent a PDF in the group for all the 7 topics that I've talked about. So I talked about charges, I talked about the Coulomb champ, electrostatic. We also talked about theorem de Gauss, potential, and conductors. I think I sent it. It's in the group. So if you need more clarity, you can go on and research and ask me. I'm available if you have any questions. and any queries, but from here, I think you can have a pleasant rest of the evening. Have you guys been given courses already?
Uncle.
Okay. Okay.
Yeah.
Okay. All right, then yeah, so this is, if you have any questions, you can contact me. I think my line is in the group, and then have a blessed rest of the day.